let's just again realize where we are, right? So you remember in this semester, we started first with introducing electric field, electric force, right, as a foundation basically. Then we decided to simplify our life, introduce the energy approach. Pretty much that was our foundation, right? And then once you lay down the foundation, then what's left to do? You just start applying that foundation to describe any electrical phenomena, right? So and we decided to go towards circuits, and that's what we've been doing for the last 3 or 4 classes, right? First we introduced batteries, capacitors, and then a method of an equivalent capacitance, right? So in order to analyze circuits where we have more than one capacitor. Then in the previous class, we introduced the idea of current in the circuit, right? And the idea of the resistance, right? And we introduced resistors, right? So now at this point, we can say we know everything about one resistor, single resistor, right? In terms of analyzing it, what does it mean analyzing a resistor? If you know those 3 parameters, right? You remember I already mentioned mentioned this circuit trinity several times. Ri delta V. If you know resistance, current, and the potential difference across a resistor, you know everything about that resistor in the circuit, right? So now we can say, yeah, we are experts. We know how we can analyze a single resistor, and we've done it in the previous class. And now, what next logical step? Yeah, what about several resistors connect several resistors? How can we analyze them? And what does it mean analyzing a circuit full of resistors? It just means that you need to find these 3 parameters, Ri, delta V, for each of those resistors. As simple as that. So if you have 3 resistors, you need to find 9 parameters, right? So, but today we're going to restrict ourselves to cases where resistors are connected either in series or in parallel. And what we're going to introduce, the method of an equivalent resistance, is very similar to the method of an equivalent capacitance. Lots of similarities, right? And every time, okay, quite often, I will reminding you guys we've done something similar when we analyze capacitors, right? And even the method which we're going to eventually use to analyze resistors will be very similar to the method of an equivalent capacitance. Okay, so now after this short introduction, let's actually start discussing it. But of course, first of all, we need to again pronounce what does it mean to use method of an equivalent resistance. It means that if you have some circuit with a bunch of resistors, but of course those resistors must be connected either in series or in parallel. If they're not connected like that, it's illegal to use this method. What can be used in that case, we will discuss it most likely tomorrow or the day after tomorrow. Yeah, tomorrow most likely, right? But anyway, so for now we assume that they're connected like that. And so the idea is you replace all those resistors with a single resistor, which we call the equivalent or a equivalent resistor, right? And when you do this replacement, the rest of the circuit, the work of the rest of the circuit must be untouched. It must work in exactly the same way. So you remember I introduced in a similar way method of an equivalent capacitance. Now I'm pronouncing the same words for the method of an equivalent resistance, right? Okay, so now let's introduce formulas which we need and important pieces of physics, right? Which we need to analyze, to apply this method. Okay, so let's start first with, okay, actually, yeah, before we start discussing actually the method, let me quickly go through circuit elements, how we represent circuit elements in circuits, right? And then we'll continue with the method of an equivalent resistance. Yeah, I should mention it. I should have mentioned it even earlier. All right, and then we'll continue with what I started. Battery, we've been using it already many times, so familiar. You are familiar. I'm of course lazy to draw this many lines. I just usually draw 2 lines only, right? A wire, doesn't matter if it's bent or twisted or in any shape. So every time it's a straight line, right? Right. It's just circuits look better in that case. Then the resistor, right? So this symbol, and as I told you, every time when I try to draw the symbol, it looks ugly. In Europe, just a rectangle is used. Then a bulb. That's the symbol of bulb, but whenever I need to draw a bulb, I usually just draw actual bulb, right? The shape of an actual bulb. I found it's easier and cooler, right? But anyway, so that's the symbol of bulb, and you will see it occasionally, right, in this course. Then junction point. So sometimes if a circuit is very complicated, there might be even kind of solid dot, right? Thick dot to tell you that actually there is a connection over there, physical connection between wires. Capacitors, we used them already, so you're familiar. And in a class or so, we will first we will see switch in our circuits when we start discussing RC circuit. Okay, I just wanted to briefly mention, but of course, most of you are familiar with these symbols, right? Okay, and now back to the actually method of an equivalent resistance. So let's start with a case when they are connected. Okay, resistors are connected in parallel. And so let's assume that we have three resistors connected like this, right? So this is our real circuit: R1, R2, and R3. And of course, they're driven with this battery, which give us potential difference of a delta V. All right. And of course, what do we have to every time introduce? We need to introduce an equivalent circuit where all these three resistors will be replaced with a single equivalent resistor. So that's our equivalent circuit. And you know what? The structure of the slides will be very, very similar to the structure of the slides which we use to analyze capacitors. So there will be a real circuit, equivalent circuit. Here we will play with three parameters, right? And then eventually the formula which will be used to find our equivalent will be here, right? So I do it on purpose so that it's easier than follow, right? If you keep the same structure of the slides. Okay, so and again, when you make this replacement, as I said, replace these resistors with an equivalent resistor, the rest of the circuit must work in exactly the same way. That's what I wrote it here. Right. So it means what? If delta V potential difference, let's say 9 volts here, exactly the same 9 volts must be there. If a certain current, let's say 5 amps, is taking from the battery in the real circuit, exactly the same current of 5 amps must be taking from the battery in the equivalent circuit. Okay, so now after pronouncing this, now let's think about those three parameters: R, I, delta V. Resistance, R, that's what we actually want to find in the end. We want to find the formula which can be used to find this R equivalent, right? So this will be at the very end, right? So it means that two parameters left, two quantities: current and the potential difference. Okay, let's start analyzing them. So first I want to ask you, which quantity out of those two, current, potential difference, is exactly the same for all these three resistors? At this point, it should be obvious for everyone, right? To everyone. So since potential differences are the same across these three resistors, basically that's why that's the test we need to run in order to convince ourselves that the resistors can, or any elements, connected in parallel. If potential difference stays exactly the same all the time, then those elements are connected in parallel. And that's what we have in our case. They're connected in parallel and potential differences are the same. If you still sort of not very confident, look, all the points on the left hand side of this circuit, all these points, right? They all belong to one big piece of metal. All these wires, electrode of the battery, so and all these wires, they belong to the same piece of metal, and of course they are at exactly the same potential. So let's say 5 volts. So all these points on the left hand side are at 5 volts. And then exactly the same I can say about the points on the left side of this circuit, right? So let's say electrode of the battery is at minus 5 volts, and then of course all these points, since they belong to the same piece of metal, they will be also at minus 5 volts electric potential. So plus 5 minus 5 plus 5 minus 5. So every time there will be 10 volts potential difference across each of these resistors. So we can write this. So delta V1 equals to delta V2 equals to delta V3, right? And equals to the potential difference provided by the battery, right? Because they're connected in series, or in parallel, sorry. Now, let's connect these potential differences with potential difference across an equivalent resistor. And in order to do that, let me make this trip. So again, delta V1 equals to delta V2 equals to delta V equals to delta V across the battery. Then, when we introduce an equivalent circuit, battery must work in exactly the same way. So it means that now we can move to this circuit. So exactly the same delta V will be here. And this delta V is across our equivalent resistor. So it means that we can say that potential difference across an equivalent resistor equals to the potential differences across resistors connected in parallel. So now I can add to this line over here, it is equal to delta V equivalent. And this piece of physics, okay, I circle it, will be used in our analysis. That will be the bridge which we're going to use to analyze circuits. Right. So we need to remember this potential difference across an equivalent resistor equals to the potential differences across resistors connected in parallel. In case of them connected in series, of course, will be slightly different. Okay, so it's first important piece of information. Now we know what happens with delta V. So now what's next? Current left out of those two parameters, right? Now we need to analyze current. So what can we say about current? So let's assume that current I is taken from the battery. And then, of course, this current will be split into three currents. Some current will go through the first resistor, then through the second, and through the third resistor. So what can be used now? Conservation of current with in the presence of the junction point. Okay, here we can draw it as one junction point, or we can draw it circuit as having two junction points. But anyway, in both cases, conservation of current will look exactly the same. So this current I will be equal to I1 plus I2 plus I3. Just current will be split into three currents, right? So as a result, we're getting this very important expression. So, and why I'm so happy about this expression, because now using this expression, we should be able to actually derive the formula for an equivalent resistance. All right. So now, since we have an expression, yeah, we can use that to derive the formula. But of course, now, since we want to get information about R at the end, derive the formula for R equivalent, so we need to insert resistances in this expression. So how can that be done? Ohm's law, which connects all these three parameters, R, I, delta V. So of course, we can insert, in this case, R in this formula. Right. So Ohm's law. We're going to use it in this form, so delta V divided by R. So I can write, so I1 equals to delta V1 over R1, but you see, I omitted a subscript next to delta V, because all delta V's are exactly the same. I immediately use this fact, right? So delta V over R1, then I2 will be delta V over R2, and of course delta and R3, I ran out of space, so I skipped that, the third current. So that's what we're going to plug to the right-hand side of this expression. So now, what about the left-hand side, I? And in exactly the same way like we did analyzing equivalent capacitance, you remember how we got this total charge or total potential difference in the circuit in method of an equivalent capacitance? We used to get it from the equivalent circuit. So now we're going to do the same. Let's find this left-hand side, this total current I taking from the battery using an equivalent circuit. Because, again, since battery works in exactly the same way, so if current I, this current I is taking from the battery in the real circuit, exactly the same current must be taking from the battery in the equivalent circuit, right? And of course, this delta V is applied across R equivalent. And this R equivalent is basically our finally unknown. So we can apply Ohm's law for this circuit for that R equivalent. So we can write that current I is taking delta V divided by R equivalent, and that's what we're going to plug into our left-hand side of this expression. So almost done. So now let's just put all these substitutions into this expression. We end up with something like that. And again, you see subscripts next to delta V are missing because they're all the same, right? I use this fact. So now all those delta V can be canceled, and we're getting the formula which most of you are familiar from high school. All right. But again, I didn't feel like just presenting the formula without discussing it, because lots of important physics can be discussed over here, refreshed, right? And then the more you use it, the better you remember and the better you understand it. Right. Okay, so now eventually, of course, we will need to use this formula for an equivalent resistance, right? And this piece of physics, that's what we will need to analyze circuits full of resistors connected in series or in parallel. Again, typical mistakes. Every semester, a few students made that mistake when they calculate all these reciprocals and call it R equivalent. Don't forget to flip at the end. When you calculate all those reciprocals, flip it in order to get R equivalent. Okay, so that's what we can get from this case, parallel case. Now let's do extremely similar to derive a formula which we will use to find R equivalent when resistors are connected in series. Right. Okay, so now let's discuss this situation. Right. So this is our real circuit. 3 resistors now connected in series, and they're driven with the battery with the potential difference of delta V. And again, so what we need to do eventually, we need to introduce an equivalent circuit. And when you again replace those resistors with R equivalent, the rest of the circuit, in this case battery, must work in exactly the same way. So, right, so exactly the same delta V over here and here, you see. And if current I is taken from the battery in the real circuit, exactly the same current must be taken from the battery in the equivalent circuit. All right. So the rest of the circuit must work, in this case battery must work in exactly the same way. Okay, so now having said that, now what next? Again, our formula for R equivalent we want to get at the end. So as a result, 2 parameters left to discuss: current and the potential difference. So which first I want to ask which, again, quantity is exactly the same for these 3 resistors. In this case, it's even more obvious, because it's basically a circuit where we don't have any junction points, and we can use conservation of current without junction point, which we introduced in the previous class, I think, on Friday. So it means that current I1 equals to current I2 equals to current I3, and it is equal to the total current, this current, taking from the battery. So we can use conservation of current without junction point. So that's right. Now, again, I want to connect these currents with the current through the equivalent resistor. So which way? So I just mentioned that a current taken from the battery in the real circuit must be equal to the current taken from the battery in the equivalent circuit. And all this current goes through our R equivalent. So current through R equivalent must be equal to this current goes through all our 3 resistors. So over here we can add that all this I1 equals to I2 and equals to I3 equals to I equivalent. So this piece of physics, again, important, and we will be using it analyzing circuits like this. So again, we need to remember that current through the equivalent resistor equals to currents flowing through resistors connected in series. All right. Okay, so now we know information about current, and now what's left? Delta V. So what can we get about potential differences across these 3 resistors? Now it's also reasonably simple. The total voltage drop across the whole circuit, okay, provided by our battery, of course, delta V, right, equals to voltage drop across the first resistor, delta V1, plus voltage drop across the second resistor, delta V2, and plus potential difference across the last resistor, delta V3. So delta V equals delta V1 plus delta V2 plus delta V3. Again, great. What I like about this is that we got an expression. So in order to derive our formula for the R equivalent. But of course, we need to introduce resistances in this expression. So how can that be done? Again, Ohm's law, which connects all these three parameters. And now I'm going to use it in this form. So delta V1, it will be R1 times I. And again, you see there is no subscript next to I because all these currents are the same. All these currents are the same. So as a result, I drop subscript immediately. So in exactly the same, I can write delta V2 equals R2I, and then delta V3 R3I. So that's what we're going to use in the right-hand side. But left-hand side, like in the previous slide, every time the left-hand sides is found in all these methods using the equivalent circuit, right? So we need to get delta V across the battery, but also it's the same delta V across R equivalent, right? So delta V across, and of course this current I also flows through R equivalent because there's only one resistor, right? So we can write that delta V equals to current I times R equivalent, just using Ohm's law. So we can grab that and shove it into the left-hand side of this equation. So after this, we just need to write this expression in terms of these substitutions, and we're almost done. So R equivalent times I, R1 times I, R2I plus R3I. All currents are the same, can be cancelled, and we're getting the formula, which most of you know, again, from high school. So eventually, in our analysis, we will need to use, again, this piece of physics important, and the formula for the equivalent resistance. Right. Okay, all right, and again, you see structure of all these 4 slides, 2 slides for C equivalent and 2 slides for R equivalent. You see structures are exactly the same. Right? Okay, so now, before I start looking at the examples, let's answer one conceptual question. And then I will switch to the whiteboard and we will start looking at 3 problems. I prepared, I think, 3 problems to discuss. Right? So let me switch to the next slide. And it's somewhat related to physics. Right? I know, 50% of physics and 50% of, I don't know, something else. Okay, so car. Headlights over car. How should we wire them? Should we wire them like this? When 2 bulbs, of course, two headlights, of course, 2 bulbs, right? Should we wire them like this in series? Or should we wire those bulbs like this in parallel? Yeah, with the same battery, right? So again, the poll is in the chat. So far I don't see you are not active in the chat, so it should be right there. Let me also switch to the chat. Now let me discuss this quickly. So let's assume that this case is used to wire bulbs. So what happens if one bulb, for example this one, gets burned out? Basically, it means that this is the broken filament, right? And as a result, it means this there is only one loop, and of course, as a result, this circuit is broken. So it will be open circuit, right? So it means that there would not be any current through this bulb. And of course, as a result, both of these bulbs are going to produce nothing. So if you use this wiring, so if one bulb is out, then you will end up in a complete darkness. which is, from safety point of view, right, of course, not the best solution, right? So now let's discuss the second case when we have two bulbs connected in parallel. In this case, now we have two loops, right? So this smaller loop and that bigger loop. So if one bulb gets burned out, well, for example, let's say this one, the top one. So of course, current to this bigger loop disappears, right? But we still have the smaller loop, this one. So through this loop, of course, now we'll have larger amount of current flowing, and so this bulb will be still bright, right? Still producing light, and it will be actually produce more light because more current will flow through this bulb. So in this case, you're not going to end up in a complete darkness. There will be still some light in front of you, and you can still safely drive. But in this case, if one bulb is out, then you are in complete darkness. And of course, from a safety point of view, this is a wrong case. Of course, it must be in parallel. Of course, real wiring is significantly more complicated, but nevertheless, it's worth of discussing and emphasizing on this simple idea. But of course, most of you got that. Okay, so that's why I told you it's more like a fun question, right? Somewhat related to physics. So now I think it's time for me to switch to the whiteboard and start discussing example. Yeah. Yeah, let me switch. Yes, so what do we have here? This problem is not from the book. I just created it, made it up with simplest possible numbers, right? And just as an example. So what do we have? This simple circuit, a battery, potential difference 3 volts. Then 3 resistors, R1, R2, and again, look, on purpose I pick R1 has 1 ohm resistance, R2 2 ohm resistance, and R3 3 ohm resistance. Easy to remember. And so the question is, assignment, we need to analyze this circuit. Again, what does it mean, analyzing a circuit full of resistors? You need to know 3 parameters about each of these resistors. Since resistances are given, it means that only 2 parameters, current and the potential difference across current through each resistor and potential difference across each of these resistors. So eventually we need to find 6 parameters. 6 parameters, I1, I2, I3, delta V1, delta V2, delta V3. Right. So again, it's a similar like what we did analyzing capacitors. Right. And also, I'm going to arrange my solution in a very similar way. Again, circuits are going to be here in the middle. I hope I will be able to fit them. Then there will be some calculations above and lots of calculations below. Again, I told you when I saw this structure of the solution in the book, and I liked it. It's one of those things which I liked about this book. Right. So let's start. So first of all, again, we need to simplify the circuit to the simplest possible, to equivalent circuit, where we're going to have a single R equivalent across this battery. And again, every time when we're going to make each step, the battery must work in exactly the same way. Right? You remember what I told you before. So now, which resistors connected either in series or in parallel? In this case, usually students see it immediately that these resistors R1 and R2 are in parallel. And again, what's the test that you have to run in order to convince yourself? Potential differences across these elements must be exactly the same all the time. It doesn't matter what you do with this resistor, which battery you apply over here. Maybe you replace this battery with very complicated circuit. It doesn't matter what you do with the rest of the circuit. If potential difference across these elements exactly the same, so then we can say, yeah, they are connected in parallel. And that is true because these points above these resistors, they are the same potential because they belong to this piece of metal. Wires are piece of metal, right? And also these points below, again, they belong to this piece of metal, so they must be at exactly the same potential. Let's say 5 volts, 3 volts, 5 volts, 3. Potential difference will be 2 volts. Right? So these resistors are connected in parallel. So let me circle them. And right, so they are in parallel. Okay, so as a result, we can simplify, make the first step and simplify this circuit to slightly simpler one. And again, the battery must work in exactly the same way. So I can redraw my circuit. So now R3 we did not touch, we didn't do anything. But instead of R1 and R2, we're going to introduce the first, and you see how ugly every time when I try to draw this resistor, it end up being ugly. So let me label it as R12. Okay, it makes sense since we replaced resistor R1 and R2, so I use their subscript to denote their equivalent resistor. Right. And this. R3 is still the same. We didn't do anything with that. So now we can calculate, of course, R12 because we derived the formulas. Parallel case, we need to deal with those reciprocals. Again, my least favorite formula. So I can use that. So it will be 1 over R12 equals to 1 over R1 plus 1 over R2. Of course, you can bring to the common denominator. Then flip it in order to get R12. At this point, I'm sure that you can do that easily. So it will be in the numerator product, R1 times R2 divided by the sum of R1 plus R2. So let me plug numbers, 1 and 2, so it will be 1 times 2. Okay, I will skip units, and 1 plus 2. So it will be 2 over 3 ohms. Right, let me check. Yeah, 2 over 3 ohms. 2 over 3 ohms. So that's R12, and let me frame it. Okay, circle it, because again, it's in a few minutes I will need it. So it will help me to find it, to spot it immediately. So now the next step. So which resistors are connected either in series or in parallel? Now it's obvious, right? So because now there are no any junction points, so current through this resistor and current through that resistor must be the same. And that's basically the test that you have to run to convince yourself that elements are connected in series. It doesn't matter what you do with the rest of the circuit over here. And if current through the elements exactly the same, that's a clear indication that those elements are connected in series. So in this case, these two guys are in series. And so now I can draw the simplest possible circuit. All right. And again, battery works in exactly the same way. Right. You know what? No, I hate it. It looks so ugly. Pretty much the same. Sorry. So that will be our R equivalent. And again, potential difference across the battery must be exactly the same. And so, yeah, we can find now the value of R equivalent because these guys connected in series. So in order to find R equivalent, we just need to add their values. Again, the previous two slides. So I can, okay, you know what, let me separate this. So now related to this, so R equivalent equals to R3 plus R 1, 2, and that is equal to R3, 3 ohms, and R12 is 2 over 3 ohms. So if you bring to the common denominator, it will be 9 over 3 plus 2 over 3. It's 11 over 3. Ohms. Right. So that's the value of an equivalent resistance. again, let me frame it. So now at this point, so how can we use this? It's like in the slides when we were deriving those formulas. Now we can use this to find total current taking from the battery. Since there's only one resistor across one battery, so current can be easily found using Ohm's law, right? You know what? Yeah, I think I have a space. I will be able to find that current over here on top. So I, and which way I label it? I think I equivalent. Yeah, let me. And you know what? No, I will just use without subscript. It just basically, you understand, it's a total current, right? So I will be equal to delta V divided by R equivalent. Delta V is given 3 volts and divided by the value of R equivalent, so 11 over 3 ohms. So that 3 in the denominator goes, of course, upstairs in the numerator. You remember how to deal with fractions, so it will be 911. So it will be 911 amps, right? 911. Let me check just in case. Yeah, 911 amp. Okay, so that's okay. I should frame it with red circle because it's a very important. So that is the total current taking from the battery. So I can draw it here. That's our I. But also, since you remember, when we make these replacements, a battery works in exactly the same way. So the same delta V here, the same delta V here. If current I over there, exactly the same current must be here, and exactly the same current over here. So now, since we simplify the circuit, yeah, we can find the total current taking from the battery. If I asked you, for example, from the very beginning, guys, could you find the total current taken from the battery in this circuit, most of you wouldn't be able to answer this question unless you deal with this lots of many times, and you can make these steps very quickly in your head. Yeah, only in that case you should be able to calculate the total current. Otherwise, it will be difficult. In that case, you will have to just repeat the steps and to find a total current, right? So there it will be difficult. But here, it's a piece of cake. All right. So now we know information about the total current. So we found at least something about this circuit. Like I I told you when we analyzed capacitors. So basically now we sort of created a small crack in the wall, right? In the wall made of those unknown quantities. And now once we made this crack, now we can open up this crack, right? In order to find to see the truth, right? And eventually to find all the quantities which needs to be found. So now at least we have this crack, and now using that we should be able to find the rest of the parameters. So now we need to start moving back, actually finding all those unknown values. Okay, so now let's start moving back and simplifying the circuits. We use those formulas for R's, this, that. Now to move back, we need to use those important pieces of physics, which I also circle in slides when we discuss these cases. All right. So first, now we need to use slides where we discussed resistors connected in series. And you remember that important piece of physics, that current through the equivalent resistor equals to currents through resistors connected in series. This is our series case, so we can use that bridge. Let me write it down. And we know the current through the equivalent resistance, right? So let me use that bridge. So I can write just I equals to I, which way I label it R1, probably I sub R1. No, just subscript 1 or 1, 2. I 1, 2 equals to, so this current is I, which we found, 911. And this is current, oi, R3, not R1. Sorry, I3, it's a current through this resistor and current through that resistor. And it is equal to 911 amps. And let me emphasize, so that current comes through from there. Okay, so that's our bridge. Now, using this bridge, we should be able to find some information about R3 and R12. So let's start with R3. So look, what do we know? We know the value of R3, 3 ohms. Now we know the current, 911. And so if you know resistance and current, can you find potential difference? Piece of cake, right? And in order to, again, use that Ohm's law properly, because every time we will have to solve it for current or potential difference, right? So that you would make silly mistakes, it's better to write somewhere in the corner so that you would rewrite it properly. So let me write it like this. So R, okay, we introduce it in this way. So delta V divided by I. Okay, so let me frame it. And so now we need to find delta V. So it's a R times I. So I can write, so delta V3 equals to R3 times I R3. And again, that current I3 comes from the bridge. Okay, let's plug numbers. R3, 3 ohms. 3 ohms times 911 amps equals to, 2711, right? Let me check my notes to make sure that I'm getting, 2711. Right, 2711. Okay, I have to invade that part of the board to put units, volts, right? So now in a similar way, we can find the voltage drop. Okay, so before we start finding voltage drop across that, look, now we can say that we finished analyzing resistor R3 because we know its value, we found its current through that resistor, and now we found the potential difference. 3 parameters. So now we know everything about R3. We finished analyzing R3, but we still have, of course, R1 and R2. So, of course, we will find it in the next step. But for now, we still need to find voltage drop across R12. So delta V12. But of course, at this point, you should be able to tell me immediately what will be the value of a potential difference across this resistor. Because the total voltage provided by the battery is 3 volts. Oh, 3 volts. So then, if you subtract 3 minus 2711, of course, you will get the potential difference across this resistor. You can do that way, but I prefer still to use Ohm's law. Right? So delta V12, it will be R12 times current through that resistor. And again, the value of the current comes from the bridge. Right. So R12, where is my R12? It's here, 2/3, 2/3 ohms times current, the same, 911 amps. Okay, I need to invade that part of the whiteboard more. So 9 and 3 can be partially canceled, so we'll have 3 times 2, 6, 6/11. 6/11, that's voltage. Okay, so now we exhausted this bridge, so we found almost everything that we can from this bridge. So now let's make the next one. Let's the next step, next bridge. So from this to this circuit. Since inside of R12 there are still 2 resistors hidden, right? So we need to reveal that information. Right, and since this resistor replaces these 2 guys connected in parallel, so we need to use different bridge. which we again discussed in, I think, in the first slide of today's lecture, right? So there, potential difference across an equivalent resistor, according to that slide, we discussed it, we proved it, must be equal to the potential differences across resistors connected in parallel. So let me write this bridge over here and use it. So okay, I will write over here. So delta V12, which is this. You see, like everything is connected. All right, so equals to potential differences across 1 and potential difference across resistor 2, and it is equal to 6/11 volts. And again, this 6/11 comes from the last line from the previous step. You see, all the steps are so nicely connected, right? So you just roll through these steps. Okay, and so now we know the voltage drop, potential difference across the second resistor. We know its value R2, so we can find current. Again, using Ohm's law, but now we'll have to find current, so it will be delta V divided by R. Right, so let me write that. So I2 equals to delta V2 divided by R2. Delta V2, again, comes from the bridge. Right. So it will be 6/11 volts divided by resistance 2 ohms. So 6 and 2 partially cancel each other, giving us 3/11 of amps. So that's the value of the current. Again, let me check to make sure that I'm, 3/11. Okay, let me finish this problem, just 10 seconds left. Right. So now we know everything about resistor 2. We knew its resistance, then we found the potential difference, and now we found current. So we're done with I2 and delta V2. Right. And so what's left now, the last current through the first resistor in exactly the same way using Ohm's law. I1 equals to delta V1 divided by R1. And again, delta V1 comes from the bridge, and the value is here. Right. So 6/11 again, volts divided by 1 ohm. So it will be 6/11 amps. Okay, done. The problem solved. So now we found all fixed parameters. And again, you see, structure is very similar to the structure which we use to analyze equivalent capacitors. And again, for me, I like it. It's very well structured. So everything is connected. This goes there. Then using this bridge, you can find potential differences. Then the final result goes to the next bridge in order to find. And then using that information inside of the bridge, you can find the currents. Right. So, nice. I like it.